Okay, hopefully not too long of a video on parametric relations and then inverses. Just so you understand the title here, like these are kind of two separate topics. So it's not like the inverses are going to be like super, related to the whole parametric thing. Like it's not going to be parametric inverses. So just a heads up, like two separate topics essentially. Parametric relations in part one, and then in part two, sort of a thing, inverses of functions, like in general. Okay. Probably could have split this up into two sections if I'm being honest. Now that I'm thinking about it, might have been a good idea to have this in two separate sections. So maybe you should think of it that way, that this is almost like two separate sections, two separate like mini lessons together. All right, so first, parametric relations. You can define functions, or more generally relations, because remember, not all relations qualify as functions. You can define them parametrically by defining both elements of the ordered pair in terms of another variable t, which we can call a parameter. So, in other words, parametric equations, you define both of your variables like separately in terms of t, like this. So here are what parametric equations look like. Our I don't want to say like our actual variables, but our variables are like x and y, but then we have this parameter of t, and both x and y are like defined in terms of t. X is equal to t plus 1, y is equal to t squared plus 2t. So this is what parametric equations are. Your two variables defined in terms of a third variable called a parameter, which is very, 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 very often t. So this first example, what does it ask of you? It asks you to do find the points determined by all of these t values. So all you're going to do is, run through all the different numbers one at a time. If t equals -3, remember a point is still going to be x comma y, right? So if t equals -3, then x is going to equal, all you got to do is let t equal -3. So it's going to be -3 plus 1, which is -2. And then your y is going to be equal to, whatever t is at the moment, squared plus 2 times t. So what's this? -3 squared plus 2 times -3. And that's +9. That's -6. So yeah, so equals 3. So I guess the overall point, if you have room, maybe you want to literally write down like -2, comma 3, but you don't have to. The point, no pun intended. The point is you got to figure out what x equals and what y equals. So like -2 comma 3. And then that's just what you do like 6 more times or something. 1, 2, you know what I mean? It's going to do that 6 more times. What just happened? What? All right. So when t equals -2, feel free to, beat me to the punch here. When t equals -2, it's going to be -2 plus 1, which is -1. And then that would make y equal to -2 squared plus 2 times -2. So that's +4 plus a -4. So that's going to be 0. When t equals -1, this is the last time I'm going to write it all out, like write out all the baby steps of the work. So what's x going to end up equaling? Well, now t equals -1. So x will now equal 0, and the y would equal -1 squared plus 2 times -1. This is 1 minus 2, so that seems correct. At this point, I would invite you to pause the video and try and try all these other ones. I mean, just kind of a heads up, I am not writing all this out again, so you certainly don't have to. I mean, I'm pretty sure you could be able to do these in your head, you know, especially now that they're not negative anymore. That makes it easier to do it in your head. But so pause the video, please, and try all the rest of the t-values, and then unpause. All right, so if you followed those instructions, it's now unpaused, and hopefully your answers match mine. If not, double check it or reach out to me, because maybe I'm wrong. I don't know, but it should be 1, 0, 2, or 1. Yeah, that should be right. 3, right? 2 squared is 4. That should be right, I think. T equals 3, so that x equals 4. Yeah, okay. So, and if I'm ever moving on to the next, you know, page too soon, I mean, it's a video, you can pause it and go back. Part B of this example says, write the pair of parametric equations in rectangular form, or, like, in other words, like a normal rectangular equation. You know, the fact that there's 2 equations that utilizes like a third variable, that's weird, or it's not what you're used to. So this is basically instructing you or asking you to try to take these 2 parametric equations and sort of like put them back together, so to speak, into like a way more typical, just normal rectangular equation. So here's what we're going to do. For this one, I guess I'll just cut to the chase, seeing as how it's a video. You're going to use some classic substitution. You're going to somehow substitute this one into the other one. But, you know that x equals t plus 1, but there's no x over here. But if you solve this equation for t, and now that like you see that t equals x minus 1, again, all you're doing is getting t by itself. And that gets you to this point, which then you can substitute that into the t's in the other equation. So the other equation can now become y equals, well, this was t squared, but now we know that t is equivalent, and it's an even-steven trade. Substitute in x minus 1 plus 2 times t, which is that, and then all you got to do now is, clean this up, because, like an even better final answer is like kind of like a standard form type thing, where you FOIL this out, distribute here, like basic distributing property here. Remember, FOIL's also technically distributing, but this is more like typical distributing, like basic distributing. This is FOIL distributing, and I'm not including all the baby steps, but when you do bubble, and you do all the FOIL, and then you simplify a little bit, this is what you end up with right here. Because, well, I'll just go ahead and say it. This would have been x squared minus 1x minus 1x, and then the plus 1. So there's some combining that happens to get that minus 2x. And then this is what happens over here, and then you combine like terms. These sort of cancel each other out. And plus 2, yeah, should be good. That's it. So that's the final answer for part B. For this one, so this one involves some trigonometry. Well, technically. And what you're going to do is, I think there's going to be some substitution, but it's not like, I don't know if you could say that it's going to be substituting one equation in for the other. Here's a very common, it's clever, maybe I'll put it this way. It's a very clever trick, but it's also very common at the same time. What you're going to do is you're going to start like a whole new equation like from scratch. That's how I would describe this strategy. You're not like manipulating, you're not like changing this equation into like your final answer. You're basically writing a whole new equation almost like out of thin air, like a whole new equation from scratch. And then you're going to substitute into this equation from these ones. So, I mean, couldn't we sub in something for sine of t? Couldn't we solve this for sine of t? Of course. Could we also, in the same way, solve this for the cosine, like get cosine of t by itself? Sure. And then substitute these ones in. And remember, sine squared is just, you're squaring the whole sine of t. So it's going to be this x over 2 quantity squared. Over here, we're kind of replacing just the cosine with y over 4. So this becomes y over 4 squared. And then just like a little bit of like, finalizing, you end up with like x squared over 4 plus y squared over 16 equals 1. Which, okay, I don't want to open up a whole new can of worms right now, but this is a very acceptable final answer. Again, I don't want to open up this can of worms too much. In the same way that, if your final answer is in like standard form of a circle, that's a pretty good final answer. This is not a circle, but FYI, it's something very, very similar. It's called an ellipse, which is a fancy word for like an oval. So anyway, long story short, this is a acceptable final answer. It's not a circle, it's something called an ellipse. All right. Quick sip of water there for me, because I think with this point in the notes, I think this is where we basically switch over to like sort of a separate topic. This could have been like a whole other video, a whole other section, like I was saying. So this is about inverses of relations, inverses of functions, if it qualifies as a function. So here's how inverse relations and inverse functions work. The ordered pair x comma y is in a relation if and only if. Yep, that's not a typo. I know you might go, it's okay, hey, look at that, Mr. Falk's an idiot. He can't, can't misspelled the word if. That's actually a mathematical thing. That is if and only if. It's almost like a two-way street. Like you have like an if-then statement. I don't want to drag this out and try to think of rack my brain for like an example of a common if-then statement like in math or something, but an if and only if statement is kind of like the statement works both ways, where if A then B, if it was also true to say if B then A, then you could just say like A if and only if B, so if and only if is when it works both ways, two-way street. So anyway, getting back to this definition, the ordered pair x comma y is in a relation if and only if the ordered pair y comma x is in the inverse relation. Inverses of relations or functions, and this might not be even like brand new to you. You might have heard me mention this earlier in a different situation, but when you have an inverse relation, kind of like an inverse tangent or an inverse sine or something. So I know I would have mentioned this before, at least quick. The input and the output are switched. That's the quickest way to say it. The most blunt way to say it. In inverse relation or function, the input and output are switched, which, just look. Input and output are switched. So a few examples, Show that f equals root x plus 3 has an inverse function, and find a rule for f inverse of x. I don't like that notation, but that is the notation for f inverse of x. State any restrictions on the domains of f and f inverse. So first, this note. A relation has an inverse function, meaning the inverse qualifies as a function if the graph of the original relation passes the horizontal line test. That's right, the horizontal line test. You have experience in your past with something called the vertical line test. Well, there is also a horizontal line test. And when that's the test to see that, if the inverse of whatever you're doing the horizontal line test on, like a graph, like this graph. See, this is the original f function, the square root of x plus 3. If this graph passes the horizontal line test, then the inverse of this is going to qualify as a function. So does this pass the horizontal line test, where you could draw a horizontal line anywhere on this graph and it would only ever hit the graph once? Yes. So this graph does indeed pass the horizontal line test. So whatever the inverse of this is will qualify as a function. But then it goes on to find a rule for that, and here's all you do. So this is the original. Let me be clear, okay? This right here is the original function. Keep in mind that f of x is really just a fancy way to replace y, the y variable. So here's the original. Starting now, I'm going to start finding the inverse. All you do to get the ball rolling is you switch x and y. How simple is that? You switch x and y, and then all you have to do after that is re-solve this for y. Here would be squaring both sides and then subtracting 3. Okay? That's it. And technically they're asking for, so you could just take this answer and now we can call this, f inverse of x. So all I did for this final answer is I just, instead of the y again, it's f inverse of x, because here's the original and here's the inverse function. And I can say inverse function because this is a function. All right? Then the last part of this, there's 3 different parts to this example. State any restrictions on the domains. So possibly in recent days, we talked about domain a little bit, maybe. If I was heads up about this lesson, maybe we already have some, some work we've done talking about, hey, what's the domain of this equation? What's the domain of this equation? Long story short, at least for this video's purposes, the domain, the numbers that you're allowed to plug in for x, domain is about x, possible x values. In this situation, it's restricted a little bit, or a lot, because you cannot take the square root of negative numbers. You'd be getting into imaginary stuff. Okay? So we're restricted by the fact that this x plus 3, back in the original f function, has to be greater than or equal to 0. I cannot be plugging in anything for x that would, like, disobey this. So this basically describes our possible domain, like our domain. And all I got to do is like solve for x, like just get x by itself. And this basically states my domain, that x has to be greater than or equal to -3. All right? There's other situations that restrict the domain. Hopefully we've talked about that, or if not, then, reach out to me. I'm going to pause the video for a second and hope that nothing messes. Alright, so the next example is saying find an equation for f inverse of x if, original f equals that. And then it's asking, does f inverse represent a function? So a little bit of a heads up, like a sneak preview, and then we'll kind of follow up with this at the end of the example. But if you do the horizontal line test on this, so look here, the horizontal line test on this would answer this question. Or if we, once we get f inverse and we look at that graph, if that graph would pass the vertical line test. But anyway, first we're going to have to find the equation for f inverse. And remember that it's the same as last time. Once I just write it with a y instead of f of x, the first thing we're going to do is what? How do we get it going in like an inverse? We just switch x and y. And for the rest of it, from there on out, you're just looking to get y by itself. In this situation, solving for y would probably mean multiplying this denominator over to the left side, which I can just, the next step after this is just to distribute. Heck, you probably could have skipped this, writing this step, but so we're going to get to here pretty quickly, multiplying y plus 1 over to the left side. And then what we're going to do is we're going to get the y's together on one side. So I'm probably going to move this x over to the right side and move this y over to the left side, and so I end up with this. Basically switching this term and this term, with each other, like moving them to the other side. And then to keep solving for y, I'm going to factor out a y and then divide both sides by the x minus 1. So this would be my final answer for f inverse, or, well, maybe better yet, I kind of ran out of room. So if you have room, you can write this answer just with an f inverse of x instead of a y. But this is essentially your final answer. And like I was saying a couple minutes ago, what you could do to figure out if this represents a function or not, you could check this graph, which, long story short, turns out to be this, and you could check the horizontal line test for this graph, or the graph of this. I mean, this is the inverse function. You could just check the vertical line test of that. Okay? And so without opening up too big of a can of worms, the answer is yes. The vertical line test, look, there's a vertical asymptote right here, just FYI. So it's not like these two graphs are going to overlap each other vertical wise. So this does pass the vertical line test. And likewise, this graph over here of the original, there's a horizontal asymptote right here. And so this would in fact pass the horizontal line test. So the answer overall to this question is yes. You can write that down somewhere. And then the last example, different kind of example, First a note, well, we're looking to verify that this function, which we're calling f of x, and this function, which we're calling g of x, we're just looking to verify that they are inverses of each other. I mean, it's kind of like, it's like a given. It's sort of like understood just by the nature of the question that they are inverses, but you have to write out the math and the sort of the stuff that verifies it, that essentially proves it. So first, a very, very important note: f of x and g of x, not just these two, but any two functions are inverses if f of g of x equals x and g of f of x equals x. So I don't know if you recognize these as like composition of functions. So these are composite functions. So f of g of x would need to end up equaling x and also g of f of x. Remember, this means we're plugging in the entire g function into the f function, and we're plugging in the entire f function into the g function. Okay? So f of g of x. Remember, if I said, like, what's f of 7? Like, here's f of x. What's f of 7? Wouldn't you just be plugging in 7 for x? Yeah. Well, guess what? F of g of x, we're plugging in not just like a 7, we're plugging in like this entire function into that x right there. So like this right here is the g function, and we're plugging it into that. And then we're just cleaning it up. So when you cube a cube root, you're essentially canceling it all out, and we're just left with the x minus 1. And then when you bring down this plus 1 right here, guess what you get? X. So far so good. Check. And then g of f of x, again, if you were just finding g of 9, you'd be just plugging 9 into x right there. But g of f of x, it's like you're plugging in this entire function, this entire x cubed plus 1, into that x right here. So this is what you end up with when you're plugging the entire f function into g. All right? And so what you're going to want to do here to clean it up and see what this ends up getting you, clean up underneath the radical first. So like, we don't really need the parentheses anymore. So plus 1 minus 1 sort of cancel each other out. And then look at this. You're left with the cube root of x cubed. Cubed root and a power of 3 sort of cancel each other out. And you're just left with x. So check, check, checkmate. Okay? And that's basically what you do in order to verify that two functions are inverses of each other. You do this, and you do this, and you need to show that they algebraically will both end up equaling x. And that does it. Oops, sorry, hit the microphone. Okay, that does it.